video, we will study some of the programming techniques used in 8085. As we know that the microprocessor, it is a programming device, so the user, it needs to have the knowledge about the programming language, the instructions, and how it can use the techniques or methods, so it can write a short and nice program in the microprocessor for various applications. So there are some programming techniques available so that the length of the program can be shortened and for the ease of the user, so that it can write short programs for it. Now, there are three techniques available in 8085. The first technique is looping. Second is counters. And third is time delay. So these are some of the techniques which are used in 8085. First, we will start with looping. This technique, looping, it has the word loop. So loop means a circle which is repeating again and again. So in microprocessor, suppose the user, it has to perform the task. He wants that in the program several times the addition is being performed. There is a long program in which addition of two numbers has to be performed again and again. So instead of writing the addition instructions again and again, what the user does, he write a short program for the addition and call that program in the main program again and again, so that the length of the program is also shorter and the task of writing such a long program is also reduced. Space is also reduced and time is also reduced because its execution is fast. If again and again we are going to store the addition instruction in the microprocessor memory, so it will require a large space for that. So spacing is also reduced and time and tiredness is also reduced. So looping is used wherever certain task has to be repeated again and again. So this looping is used to instruct the microprocessor to repeat the task, and a loop is set up by instructing the microprocessor to change the sequence of execution and perform the task again. Suppose this is our main program we have written in the microprocessor memory, and there is a short program for addition. This is for addition. And this program has been written in certain other memory location, and this main program is written at certain other memory location. Suppose it's written at 8000 and this addition program, it is written suppose at 7000 memory location. So in this main program, wherever we want the addition task to be performed, we will call this memory location, or we will call this short program, and here we will use the instruction jump and jump 7000. Okay, so when the microprocessor it is executing the instructions in the main program, when it will encounter this instruction jump, it will jump to this position 7000. It will run the instructions which are written there, execute the addition, and in this here we will have the return instruction, and this will again return to the main program, and there we have written the other instructions of the main program. Now again we want addition. We are going to write jump 7000. Again this addition program will be run and returned to the same main program. Then further instructions will be executed. So instead of writing these 10 lines for the addition program in the main program, we are writing those 10 instructions in at a certain other memory location, and we are again and again calling that program, the subroutine which is written to the other location, and then we are running it. So this will because if we write those instructions 10 lines again and again, so it will require a large space in the memory, and if we are writing it at the other space, it will require some less space. So this is how a loop is set up, which is instructing the microprocessor to change the sequence of execution, because it is changing. Here it is jumping from this location to this location, so it is changing the sequence of the execution, and it is performing the task again and again. So you have seen that this looping is accomplished by using the jump instruction. Now the loops which are set up in 8085, they can be classified into two categories. One is continuous loop and second is conditional loop. So there are two types of loops in 8085. Continuous loops are those loops which are repeating the task continuously. That is, whenever this loop is set up, that loop is going to continuously repeat itself. It's not going to stop. Whereas the conditional loops, they are based on certain condition, that when this condition is fulfilled, then this loop is going to run, and when this condition is not fulfilled, then the loop will stop. So there is a mechanism for stopping the conditional loop, but the continuous loop, they cannot be stopped. So this is the difference between the continuous loop and the conditional loop. So let us study one by one the continuous and the conditional loop. First, we will start with continuous loop. A continuous loop, it is set up by using the unconditional jump instruction, because we have studied here that looping, it is accomplished by using the jump instruction JMP. It is the mnemonic for the jump, JMP. So when we are having this continuous loop is set up by using the unconditional jump instruction. So unconditional jump instruction is the mnemonic for it. Mnemonic means we are writing the programs in the 8085 using the assembly language. So for every instruction we have a mnemonic. For jump instruction we have the mnemonic JMP and its operand, because every instruction it has an opcode and an operand. So opcode is jump and operand is a 16-bit address here. So wherever location the subroutine it has been written there. Subroutine means from the main program we are writing a short program at certain other location. So that short program which is written at different location is called the subroutine. So the 16-bit address where the subroutine is written here, that will be the operand in it. So for example, like jump 7050H. H means it's in hexadecimal notation. So at this memory location, we have written a program, suppose for addition or for subtraction, and we will write that address at in front of this jump instruction. So in the main program, whenever we are writing this jump 7050, so that subroutine will be called, and then that subroutine will be executed by the microprocessor. So continuous loop it is set up by using the unconditional jump instruction, and this is the mnemonic or format for writing the jump instruction. Now if we draw the flow chart for this continuous loop, how it is running, we can have so this is the flow chart for the continuous loop. We are starting the loop, then it will perform the task and then go back and repeat the task. So you can see that the task has been repeated for infinite times. Once the microprocessor is entering this loop, it will run this loop for infinite times, because there is no condition or nothing is written in this loop which will going to stop the loop or the programming. So how, if once it is the microprocessor it is encountering a continuous loop, how it is going to come out of that loop? It will run for infinite times, so we cannot run the microprocessor further. So the microprocessor or this loop can be stopped by resetting the uh, function, by resetting the microprocessor IC. So by resetting it, we can stop the continuous loop. So a program which is having a continuous loop, it can be stopped by resetting the microprocessor. So if you want to stop, you have to reset the system. So this was the continuous loop. Now second type of loop was conditional loop. Now in continuous loop, we were using the unconditional jump instruction. In conditional loop, we will use the conditional jump instruction. Now, conditional loop, we are using the conditional jump instructions. And what conditions we are entering here? We are checking the flags. In 8085, we have 5 types of flags: sign, zero, parity, carry, and auxiliary carry. So, out of the 5 flags, 4 flags are used: zero, carry, sign, and parity. Auxiliary carry is not used here. So, we have conditions in associated with it. We have conditional jump instruction associated with each of the flags, and those conditions are used. If that condition is fulfilled, then the loop will be run, and if that condition is not fulfilled, the microprocessor will stop the loop and will come out of that program. So these instructions, they check the flags and repeat the specified task if the conditions are satisfied. It will not repeat the task if conditions are not satisfied. So here we have a conditions. Now for every flag we have a condition, we have a conditional jump instruction. Like for zero flag, we have jump on zero JZ. Then we have jump on no zero. So if the result after any arithmetic or logical operation, if the result is coming out to be zero, then we can have this condition. Then if the result is zero, if the accumulator register is having zero contents, then jump on that location. Or if the answer is not zero, then jump on different location. Now for carry flag, we have like jump on carry, jump on no carry. For parity, we have jump on parity odd and jump on parity even. For sign flag, we have jump on positive and jump on negative. So we have here jump on minus. That means if the answer is a positive number or if the answer it is a negative number, then we have the jump instructions for it. Okay, so for every flag we have the conditional jump instructions. We can use these conditional jump instructions to set up a conditional loop. So when that condition is fulfilled, the loop will be repeated. When then condition is not fulfilled, the microprocessor will come out of the loop and will stop that task. It will not repeat the task continuously. So this is how the continuous loop and the conditional loops, they are set up in the 8085. Now there is another type of loop which is including the indexing and along with the counter. So the counters and the looping, they are interrelated with each other. We can also set up a loop using a counter. So this is, we can say that the conditional loop which is having a counter and indexing. So how a conditional loop is set up using a counter and the indexing. Let's study about it. So here we are having the indexing technique which is being used with the counter. So what is an indexing? Indexing means pointing or referencing objects with sequential numbers, because by counter you means that something which is counting a number. So indexing is pointing or referencing to the objects which are with the sequential numbers. We are pointing towards, or we are referencing toward an object, or we can say a register or a memory in microprocessor, we are pointing towards it using sequential numbers, using a numbers technique like 0, 1, 2, 3 we are using. So this was indexing, and indexing is used along with the counter to set up a loop. So in indexing, what we are doing, the similar bytes, they are stored in the memory location, means similar data is stored in memory locations, and those data bytes are referred to by their memory locations. Those data bytes, they are called by using their memory locations. Let's see the flow chart for it, that how we are using the indexing along with the counter, and a loop has been set up through it. So first we have the start. So this is the flow chart for the counters, flow chart of indexing along with a counter. So in indexing, what we are doing, first starting the loop, then initialization is there. We are going to initialize a register with a counter, or initialize the register with a number, and then data acquisition, data processing, temporary storage of partial results if there is any arithmetic or logical operations and there are some intermediate data which has to be stored, or the intermediate results you have to store. So there is the temporary storage of the partial results. Then getting ready for the next operation. Then comes the decision making, that are all the operations in this loop they are complete. If they are complete, then display the output and stop the loop. Otherwise, again acquire the data acquisition, data processing, then repeat all the tasks. So in indexing, what we are doing, we are repeating a certain task and we are pointing or referencing towards the object using a sequential numbers. Here we are initializing certain register or memory with a number, and again we are pointing towards that register and memory, and we are repeating those tasks there, written there. And if all the tasks are complete, then it will display the output and it will stop the loop. Otherwise it will again repeat the same thing. Now this was indexing. Now how indexing is done, using a counter. So let's study the counters for it, the counters technique. So by the name counter, you can understand that the counter is something which is counting a number. Okay, we are having a technique or a method which is counting something. So counter is designed by loading an appropriate number. We are going to load a number into one of the registers. In microprocessor, we have the 6 registers B, C, D, E, H, L, and these are the 3 pairs in it. So in any of these register, we are going to load a number. We are going to we are going to copy a number, and then we are starting the counter, and using the increment and decrement instructions, we will make the microprocessor to count that count which are giving us. Suppose we are loading this B register with the number 10, and we want that a task has to be repeated 10 times. Okay, so we will write the task with the operation, like any arithmetic operation, addition. Take an example that we want that addition should be performed 10 times. So we will write the instructions for that. We will start a counter. We will initialize any of the register with 10, and then we are going to decrement that counter till that counter is 0. So 10, 9, 8, 7, that times the count, that addition task will be repeated. And when this register becomes 0, the counter becomes 0, then the microprocessor will come out of that loop. So you can see that addition of the numbers, it has been performed 10 times. So using increment and decrement instructions, we can have the counters, and we can set up a loop also. So if we see that using the counters, a loop has been established. So a loop is established to update the count. The count will be updated every time we are initializing the counter. Then we are, every time in the loop, we are updating the count. And then at the last of the loop, we are checking that whether the count has reached the final number. If we want, like, instead of starting from 10 and decrementing it till 0, we can also increment it, like starting from 0 and coming till 10. So increment and decrement we can check here, and we will see that the final number has been achieved or not, final count has been achieved or not. If it is not achieved, then that loop will be repeated again and again. If the final count has been achieved, then the microprocessor will come out of the loop. So in this way, a loop has been established using the counters. Now, if we draw the flowchart for it, then what it is, we will start with initializing the counter. So this is the flowchart of a counter. What we are doing in the first step, we are initializing the counter. Then we are displaying the count, that this time the count is this. Every time we are displaying the value of the count. Then we are updating the count, either incrementing or decrementing it. Then we are checking that is this our final count which we want. If it is yes, then it will come out of the loop. If it is no, then again it is going to display the count, update the count, and then repeat the same process up until we have achieved the final count value. So this is how the counters they work. But in this counter, we have a major drawback that this speed of processing the counter by a microprocessor, it is so fast that we are only able to see the last count. Okay, suppose we are starting from like 8,000. Okay, and every time we are decrementing, so the processing speed of microprocessor, it is so fast that we are going to get the display only zero. We are decrementing every time, and last we are going to see within a seconds that the final count has been achieved and it's zero. We are not going to see every time that it has become 8,000, then it has become 7,999. Every step we are not going to see. So this is the major drawback in the counters, that we are only able to see the final count value. So its drawback was that the counting is performed at such a high speed that only the last count is observed. So to observe the count, we have to use another technique or another method. So to observe the counts, there should be any method available so that we can check at every step that how the counter is decrementing or incrementing. So this new technique is time delay. So time delay is what it is giving some time to us in at every count. There should be some time delay so that at every step we will be able to update, or we will be able to see that how the counter is incrementing or decrementing. So another technique available in 8085 is time delay. So let's study that how the time delay is being introduced between two counts so that we will be able to observe the counting process. So in time delay, we are loading the register with a number depending upon the time delay, like how much time delay we want. So depending upon the time required, we will load that number into the register. So a register is loaded with a number depending upon the time delay, and then that number is decremented again and again, and when it has reached zero, then the loop has been come out. So depending upon the time delay, so this time delay technique, how it is used, first we are loading the number depending upon the time delay which is required. So first we will calculate the time delay, the time how much we require. So that according to that time delay required, we will calculate the number, and that number will be loaded into the register. Now every time the register will be decremented until it reaches zero. So that number which is being loaded into the register, that number is decremented, and when that number has reached to zero, then that loop or the microprocessor, it will stop further its operation and will come out of the loop. Now, how this loop is being set up, this loop is set up by using the conditional jump instruction. We will use the condition that jump on no zero. So jump on no zero, again the loop will come, because here we are initializing, suppose we are initializing the B register with 10. That 10 times we have calculated that something approx like 0.2 second time delay we want. So for 0.2 seconds we will have to start a loop with the number 10. So this 10 will be decremented in the loop like DCR B. So this B register will be decremented, and when this register has become 0, the loop will be stopped. If it is not stopped, then again that B register will be decremented, and this time. So in this way we are providing a time delay in the program. So this time delay will create some gap between the instructions, and then we can see that how the counter is being processed in the main program. So this loop is causing the delay depending upon the clock period of the system. Now, there are various techniques in this time delay, that how we can, various ways in which time delay can be introduced in the program. Like time delay using one register, time delay using a register pair. There are different types of ways in which the time delay can be introduced. First, we will study the time delay using one register. So in this technique where we are using a register, the count is loaded in a register and the loop is executed until the count reaches 0. So in the microprocessor, we have the registers B, C, D, E, H, L. And all these registers, they are 8-bit registers. So using this type of technique, which where we are using one register, we can have an 8-bit maximum number, and that 8-bit number can be used as the maximum count. So if we see the flowchart for it, we will have So this is the flow chart, how we are introducing the time delay using one register. First, we are loading the delay register, that is we are initializing the register with the count or with the time delay which we required. With that number, we are initializing the register. Now in the loop, we are decrementing the register and we are checking that whether the register is 0. When the register is equal to 0, it will come out of the loop. If it is not 0, then again the register will be decremented until it has reached the final value, that is the 0. So let's take an example related to it. Here we are initializing the C register with the count F. H means it's in hexadecimal notation, and here we are having the maximum 8-bit count. The maximum 8-bit number is FF, in hexadecimal notation. So with the maximum number of maximum time delay, we are loading this C register with FF. So in C register we are having the number FF. Now we have to decrement the register. So here we are introducing a loop, and we will write the instruction DCRC. We are decrementing this register. Then we are here placing the conditional jump instruction, that is jump or no zero to loop. Loop is what? This memory location. So when we are going to store this program in the microprocessor memory, suppose we are storing it at 8000. So this is 8000, this is 8001. Then suppose this is coming out to be 8010. This loop, this instruction DCRC, this is 8010, and where the loop has been written here we will have 8001. So when this condition DCRC then jump on no zero, it's not satisfied, that is the C register has not become 0. Like first it is FF, then it will become FE. Okay, in this way it will be decremented up till its value has become 0 0. So when this condition is satisfied, it will come out of the loop. So this is same like this flow chart. We are loading the delay register. Here the delay register is C, and then we are decrementing this register DCRC. Then we are checking that is this register 0 by using the conditional jump instruction JNZ, and then we are checking that whether this register is 0. If it is not 0, then again decrement it. We are using the loop here, and if it is 0, then come out of that loop. Now how we are going to calculate that how much delay this program it is providing? How this, if these instructions, these three instructions are written in the memory of the microprocessor, then how much time delay it will provide? Okay, because here we are loading this register with the number FF. So how much time delay? How we can calculate this? Let's see. First, if we want to calculate the time delay, then we will have to calculate the time required to execute all the instructions. First, we will calculate the time required to execute this first instruction MVIC then we will see that how much time this DCRC is taking, how much time JNZ is taking, and how many times this loop has been repeated. So first we will calculate the time required to execute the instructions which are written outside this loop, because outside the loop whatever instruction is written that will be executed only one time, but the instructions which are written in the loop they will be repeated that many times, the number which we have loaded here. Because this is FF, then it will come to FE, again these instructions will be executed, then it will reduce further like 10 9 8. In this way the number is getting reduced every time. So this is what, this is 256 times this number has been repeated, because FF when we convert it, it becomes 255 or 256 times. So 256 times this these two instructions has been repeated, or every time they are executed. So first we will calculate the time required to execute the instructions which are outside the loop, then we will calculate the time required to execute the instructions which are within the loop, and then we are going to add both the times, and then we will get the total time delay. So first we have the time required to execute the instructions outside the loop. So how we can check the time? We will first calculate the T states. This is MVICFF, so it will require 7 T states. You can approximate get this when if you know have the knowledge about the machine cycles, because in machine cycle we draw the timing diagram for every machine cycle, and we know that we have 5 machine cycle. Opcode fetch, it require 4 t states, then memory read, memory write, input output read, input output write, they require 3 t states. So this instruction MVIC this is what, it's a memory write instruction. Memory write operation is there. So first 4 t states for the opcode fetch machine cycle and 3 t state for the memory write machine cycle. So total we have 7 t states for this. Then we have DCRC. This requires only the opcode fetch machine cycle, so it will have only 4 t states. Then this instruction JNZ loop. So what we are getting first is opcode fetch, then it is memory write machine cycle, 2 times memory write machine cycle. So total we have 4 plus 3 plus 3, that means 10. So we have 10 machine cycle. Now every time this is requiring 7 machine cycles. Okay, last time when this count has been reached to 0, so this microprocessor, it will come out of the loop, it is not going to execute the last t state. So we are getting both the 10 and 7. We are going to take 7 for the last count and 10 for all the remaining counts. So this is, we are writing the t state for every instructions, because t state is what, it is clock period. 1 t state means 1 clock period. So we know the clock period because we know the clock frequency. We know clock frequency of 8085 is 3.5 megahertz. So by the clock frequency we can calculate the clock period, and by the clock period we can calculate the t states, how much time it is taking. So this is how we are calculating the time. So first let's see, suppose I am taking the clock frequency as 2 megahertz. This can be given to you in the questions which are related to the time delay calculations. If it is not given, then you can take the standard clock frequency of 8085. Here we are given that the clock frequency is 2 megahertz. So we can calculate the clock period. Clock period is what? 1 by f, that is 1 by frequency. So it will be 1 by 2, or we can say it is 0.5 microseconds, because here you can see that the frequency, it is given in megahertz. So when you calculate the clock period, it will be in microseconds. So the clock period is coming out to be 0.5 microseconds. Now outside the loop we have the instructions MVIC, FFH and DCRC. This instruction is taking 7 t states, and DCRC, it is taking 4 t states. This is inside the loop here it is starting. So outside the loop we have 7 t states. So 7 into 0.5 will give us the total time taken by to execute this instruction. So time to execute MVI instruction, it is 7 into 0.5. Because clock period is 0.5, 1 clock period is equal to 1 t state. So 7 into 0.5 will give us the total time. So this is 7 into 0.5 is 3.5 microseconds. So this we have calculated the time required to execute the instructions outside the loop. Now comes the time to execute the loop. This we will denote as TL, time required to execute the loop. So this will be the clock period into the loop t states and n to the base 10. Okay. What are these? This is the formula for calculating the time required to execute a loop. Now here, clock period, it is t, the system clock period. Loop t states, okay, t states, total t states there are in the loops, and n10, it is the equivalent N10 is the equivalent decimal number of the hexadecimal count which is loaded in the delay register. So you are seeing that we have loaded the C register with the count FF. Now this number FF, it is in hexadecimal notation. And we have to convert this hexadecimal number into the decimal number. So N10 is the equivalent decimal number of the hexadecimal count which is loaded in the delay register. So here we have FF, so it's hexadecimal count. If we convert this, it will come out to be 255. Okay, so let's put the value in this formula for TL, that is the loop delay. So we have TL equals to the system clock period. Clock period is what? 0.5 microseconds. So we will write here 10 raised to the power minus 6. Then the T states. So in the loop we have the instruction DCRC and JNZ loop. DCRC was taking 4 T states and JNZ loop was taking 10 T states. So 10 plus 4, it is total T states are 14. Then we have the N10, the equivalent decimal number, that is 255. So the loop delay is coming out to be 1785 microseconds. Or if we convert it in the millisecond, then it is approximately 1.8 milliseconds. So we have calculated TL, the loop delay. We have calculated the time required to execute the instructions outside the loop, which is 3.5 microseconds. So we will add both these so that we can get the total time delay. That was 3.5 microseconds plus 1785 microseconds. So this is approximately 1789.5 microseconds. Okay. Now there is a special note in it. You have to note this thing, that this instruction JNZ, this is a conditional jump instruction, and we have written the T states as 10. When this conditional jump instruction, it requires 10 T states, but when the loop, because loop is running for 255 times, when the last time it is running, because we are checking the condition that when it is 0, so when the loop was decremented for the last time, when it has become 0, this instruction, it will require only 70 states. So 255 times it is requiring 10 T state, but at the last time it is requiring only 70 states. So this difference, 10 and 7, the difference is 3. So the difference of these 3 T states we have to minus from this total time delay, because we are taking here 4 plus 10 we have taken here total t states as 14, but last time it is run for only 7 t states. 3 t states it is running less. So these 3 t states time we have to minus it from the loop delay. So when we are checking here, note, there is a special note in it that so the T states for the jump instruction, they are shown as 10 oblique 7. 10 when the loop is running and 7 for the last time of the count. Because the 8085 microprocessor, it requires 10 T states to require the JNZ instruction when it jumps and changes the sequence of the program. So when we are writing the program that DCRC and jump on no 0 to loop, and we are having the loop here. Loop means the address where we are storing the opcode, the machine code for this DCR. So what the microprocessor is doing, it is changing the program sequence. It is jumping again and again up till this C is 0. So to execute this instruction, microprocessor is requiring 10 T states and 7 T states when the program falls through the loop and goes to the instruction which is following the JNZ. So when at the last time when this counter is decremented and it has become 0, so this condition is not fulfilled, the microprocessor will come out of the loop and will execute the next instruction written after it. So at that time it required only 70 states. So the difference of these 3 states, it has to be subtracted from the loop delay. Now in this example which we have taken, the loop is executed 255 times, but so this loop is executed 255 times, but in last cycle it will take only 70 states. So we will now calculate the adjusted loop delay. So adjusted loop delay will be the loop delay minus the 3 t states time. So 3 t states into the clock period. So TL was coming out to be 1785 microseconds minus 3 into 0.5 microseconds, the clock period. So we will have here 1785 minus 3 into 0.5 is 1.5 microseconds. So we will have 1783.5 microseconds. Okay, we have the total loop delay minus the 3 t states time period, we have minus it. So the total delay, it will now become time required to execute the instruction outside the loop plus the loop delay. So we have total delay. Time required to execute the instruction outside the loop was 7 into 0.5, that is 3.5 microseconds we have, plus this loop delay, corrected loop delay is 1783.5. So we are getting here 1786.5 microseconds. Earlier we were getting 1789 microseconds when we have not considered the 3t states time. So at that time we were getting the total delay as 1789.5 microsecond. But after correction we are getting 1786.5 microseconds. So the difference of this 3 microseconds difference is there, and this difference can be neglected. Loop delay was TL, and the corrected loop delay, the adjusted loop delay we have, the difference is only approximately it's 2 microseconds. So it can be neglected at many times. But whenever you solve questions based on this time delay calculations, then you should consider the difference of this 3t steps. Okay. So this we studied the time delay where we are using only one register, because you know that the registers, they are of 8 bits. So maximum count which we can load into the register is FF. This is the maximum 8-bit number which can be loaded into the register, and maximum time delay we have calculated here. Now there is also another technique through which we can introduce the time delay. This is time delay using register pair. So in microprocessor 8085 we have B, C, D, E and HL. These are the 3 register pairs. So these 3 registers pair, they are of 8-bit. 8-bit means total is 16-bit. So we can maximum we can upload a count of F, F, F and F. This is the maximum 16-bit number. So the maximum number which can be loaded into the register pair is F, 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 F. Okay. This is in hexadecimal notation. Because maximum delay when we are using a register, it is only 8-bit number which can be loaded, and maximum delay it was providing was 1785 microseconds. Now if we want more time delay, then we can use a register pair, so it will give us more time delay in the program. So the time delay can be increased by setting a loop and using a register pair with a 16-bit number, and maximum number is FFFF. Now this 16-bit number, it is decremented in the loop, and when it has reached to 0, then the microprocessor, it will come out of the loop, and then that much time delay has been introduced into the program. So this 16-bit number, it is decremented by using the DCX instruction. Earlier we were using DCR, because we are decrementing only one register. If we want to decrement a register pair, then we have to use the instruction DCX here. So this 16-bit number, it is decremented by using the DCX instruction. So the 16-bit number, it is decremented using the DCX instruction. Now this DCX instruction, it is decrementing the number till it has become 0. However, because we know that we have flags in 8085 and one of the flag is the 0 flag, and this flag is set when the result is 0, but that result has to be in the accumulator, and here we are using the other registers B, C, D, E, H, L. So we cannot use the condition on the 0 flag, or we can check this flag that when this flag is 0, then this condition is not satisfied and the processor will come out of the program. But because this flag is affected only when the result in the accumulator is 0. Now we have, let's take an example that how we can get a time delay using a register pair. Now, as we have said here that this 0 flag is set only when the accumulator result is 0. If we want to set this 0 flag, then we have to use a technique so that this 0 flag is set. In this program, we have taken one of this technique. We have used this technique to set this 0 flag. Now here we have loaded the BC register pair. Here B is written. So we have loaded the BC register pair with a count 2384. This is a 16-bit count. So this 2384, it will come into the BC register pair. Then we are going to decrement this register. So it will now become 2383. BCX is used, so register pair will be decremented. Then we are going to move the C into A. The C, content of the C register will be moved into accumulator. So accumulator has now become as 83. Now we are going to OR the accumulator with the B register. So this B register is what? 23. So both these registers, they are going to OR so that the 0 flag is set. This will be OR when both the contents will be 0, 0, 0. That is, accumulator has also become 0 and B has also become 0. So when the contents of the accumulator are 0, then the 0 flag will be set. So this is also one of the technique to set the 0 flag and to have this condition satisfied. So jump on no 0 to loop. When it is not 0, it will again decrement the B register and then move again the C register into accumulator or the contents of accumulator with B, and again if it is not 0, then the loop will be repeated. So this loop will be repeated until the contents of the accumulator are 0. Okay, and when this 0 flag is set, so we can write here So this OR instruction which we have written, that ORAB, that is OR accumulator with B, it will set the zero flag only when the contents of the B and C registers, they are simultaneously zero. Because C we have already moved in accumulator, so in accumulator we are having the contents of the C register. So when both C and B are zero, then only the zero flag is set. If one of them is zero, then zero flag is not going to set. Only when both are simultaneously zero, then only the zero flag will be set. So we can say that the loop is repeated 2384 times, 2384 times, equal to the count which is set in the register pair. Here we have loaded the BC register pair with 2384 count. So this much time the loop will be repeated. Now how we can calculate the time delay which is introduced by this register pair, this 2384 times count, how much time delay? The formula is same which we have used earlier. So we have to calculate the time delay to execute instruction which is outside the loop. Okay, so outside the loop we have LXIB 2384. First we will calculate the T states. LXIB will require 10 T state. DCXB it will require 7 T states. Then move A comma C, it requires 4 T states. DCXB, sorry, it will require 6 T states. Move A comma C 4, or B it require 4, J and Z it will require 10, and correction will be 7. So we have 10 T state for the instruction outside the loop. So 10 into the clock period. Suppose the clock frequency given to us is 2 megahertz. So we are getting 0.5 microseconds. Okay. Now for the instruction inside the loop, we will have this clock period 0.5. Then we have the total number of T states. So T states are what? 6 plus 4 plus 4 plus 10. So it is 10, 10, 24. 24 T states are there, multiplied with the N10. That is the decimal equivalent of the hexadecimal number. Here hexadecimal number is 2384. So we are going to calculate the equivalent decimal number. How? We are going to multiply it with 16 to the power 3. This is 16 to the power 0, 16 to the power 1, 16 to the power 2, and 16 to the power 3. So 3 into 16 to the power 2 plus 8 into 16 to the power 1 plus 4 into 16 to the power 0. So its decimal equivalent comes out to be 9092 with base 10. So here we are going to multiply it with 0.5 into 24 into 9092. So it's coming out to be approximately 109 milliseconds. So this is 109 milliseconds. Now here we have taken the total T states. We have for JNZ instruction also we have taken 10 T states, but last time it is executing only using only 7 T states. So for 3 T states we have to adjust this loop. So total delay will be this TL plus this outside the loop which we are taking, so representing it with T naught. So this minus the 3 T states time into clock period was 0.5. So this we have calculated 109 minus 3 into 0.5, so 3.5, but this is in milliseconds and this is in microseconds. Okay, so this is 1.5, so you have to adjust this delay also. Okay, this is adjusted loop delay. So this is how we use the technique time delay using the register pair. Now third way of introducing the time delay is time delay using a loop within a loop technique. We are having two loops, one is the outside loop and another is the inside loop. So we are having two loops, one into the other, and those loops are introducing the time delay in the program. So we have third way as time delay using loop within a loop technique. These techniques can be used in the increasing order of the time delay required. If we require less time delay, then we can use time delay using a register. If we require more time delay, then we can use time delay using a register pair. If we require further more time delay, then we can use this loop within a loop technique. Let's take an example here. So here the we have to move the first B register with this 38H, and C register is having FF, this number. Then first we will decrement C register. This C register will be decremented. It will become F, E, F, D in this way. And when this C register is 0, then next instruction will be executed, otherwise it will be decremented up till its value is 0. So the inside loop, it will be repeated 255 times because FF, its decimal equivalent is 255. So 255 times this inside loop will be repeated. Now when the C register is 0, the microprocessor will come to this instruction DCRB. It is now going to decrement this B register. If it is 0, then it will come out. If it is not 0, then it will jump to this location. Again it is going to initialize the C register with FF, that is 255, decrement C register, going to execute the inside loop up till its value is 0. Again it is going to decrement the B register. Now B is what? 36. No, it is not 0. Again it is going to initialize the C register. So you can see that the inside loop, how many times it is repeated? For one time it is repeated 255 times. Now B, it is 38. So 38 times 255 times the inside loop is repeated. That is 38 into 255. Okay, so this much time delay is being provided by using the loop within a loop technique. So you can see that this is providing a very long time delay in the program, because every time the B is decremented inside, every time the C is initialized to 255 and it is repeated. So 38 times 255 times inside loop is repeated. Okay, now how we can calculate time delay in this case? First we will calculate the delay in inside loop. that is loop 1. Okay, so inside loop we are having is MVIC, FFH, DCRC and JNZ. So these three instructions, this is having T states as 7, this is 7, 4, 10 by 7. DCRB will have 4 T states and this will again have 10 by 7. So using the same formulas, we can calculate the inside loop, that's loop 1 time delay. So it is coming out to be, we have already calculated it, 1783 microseconds. We can have denoted as TL1. Then loop delay due to the loop 2, it is, we have 38H, the outside count. So when we are going to convert it in decimal, it is equivalent to 38H, that is hexadecimal. It is equivalent to 56 in decimal notation. So 56 into this TL1, because inside loop is also repeated in it, plus we have the inside outer T states, we have 7, 4 and 10. So 21 into 0.5 the clock period. So it will come out to be 100.46 milliseconds. Now we have the total delay, because here we have considered all the instructions. So total delay will be the TL2 plus the delay due to this instruction MVIB, because it is outside both the loops. So we have MVIB instruction 70 states into 0.5 microseconds. So this is the total delay which we can calculate here. So you can see that how the time delay using a loop within a loop technique can be introduced and how we can calculate it. If we draw the flow chart for it, then its flow chart will be like, first we were loading the register B, then we are loading the register C, first we are loading the register B with the count 38H, and then we are loading the register C with FF, then we are decrementing the C register, checking that the C register is 0 or not. If it is not, then decrement it. If it is 0, then decrement register B and check that is register B is 0. If it is 0, then come out of the loop. If it is not 0, then again load the C register with FF and decrement this. So this is how the loop within a loop technique, and we are introducing the time delay using it. So you can see that this loop within a loop technique is just introduced to increase the time delay. Register pair, we can have the maximum time delay, maximum count which we can introduce using a register. Single register was FF, because it is the maximum 8-bit number. Then using the register pair, we can have the maximum number as F, F, F and F. But if we want more time delay, then we can have this register, this loop within a loop technique. So this was the third programming technique we studied in 8085. So in this whole video, we studied the programming techniques of 8085 which are frequently used. First was looping, then counters, then time delay. These three are interrelated with each other. We use loop with a counter, and in counter we can introduce the time delay also. So these three are interrelated with each other. So I hope this video is clear to you. Thank you.